there will be a chair, so I think I'm gonna chair myself. My name is Rafael Rabelo. I'm from the State University of Campinas in the state of São Paulo. And I would like, before I start, I would like to thank the organizers for well, yeah, someone please tell them that I would like to thank them for it's always a pleasure to be here in Natal. And today I'm going to tell you about this quite simple idea that led to some very interesting counterintuitive results, at least according to my intuition. This is joint work with Tassius Themistocles and Marcelo Terra Cunha. This idea, this simple idea that I said is related to how, when you impose strong constraints on the measurements that you're making on your systems, these constraints being compatibility constraints, how instead of losing, you actually have an advantage. So you gain more than you lose when you impose these quite strong constraints. This I hope this will be clear the remaining of the talk. So, well, in the sense of Bell non-locality tests. So, for starters, this is one thing that you've seen a lot in these couple last days. A usual Bell scenario, bipartite, where two parties they receive parts of a composite system and perform measurements on them. The measurements of one party, party A, Alice, are labeled by X, party B are labeled by Y, the results are A and B. If they know nothing about the systems or the measurements they're performing, the best description they have about this experiment is given by this joint probability of obtaining outcomes A and B, given that the measurements were X and Y. In general, there will be correlations. So this joint probability will not factorize into the product of the marginals. And as we've seen in previous talks, the locality assumption, the local causality assumption by Bell, means that these correlations will be local if they can be written like this, like a convex combination of probabilities of outcome A that depend only on measurement X and some hidden variable lambda, and the same for B. The simplest scenario is when both parties perform only two possible measurements, and each measurement has only two possible outcomes. This is the usual CHSH scenario. We can define the correlators of measurements X and Y. This is given by the probability of outcome A being equal to B, minus the probability of outcome A different of outcome B, and then we know that the only relevant Bell inequality in this scenario is the CHSH inequality. So up to relabelings of outcomes and measurements, this inequality is necessary and sufficient for you to know if your correlations are local or non-local. So if you violate this inequality, then you have what we call Bell non-locality. Now, if you go to a little more complex scenario where we allow Bob to perform M measurements instead of only two, does anything change? Well, not actually. Stefano Pironio showed that even in this scenario, the only relevant Bell inequality up to relabelings is the CHSH inequality. So you can increase like the number of measurements of one of the parties, that this is still the only relevant Bell inequality that you have. So keep this in mind. We know that at this point, quantum systems violate Bell inequalities, but you need at least two ingredients to have to observe non-locality in quantum systems. The first of them being entanglement. So you need the state of your system to be entangled, meaning that it cannot be separable. It has to be different than not equal to a convex combination of product states of the parties. However, we know also that entanglement is necessary but not sufficient. There are entangled states that do not violate any Bell inequality. This is a result by Werner from '89. And the Werner states, the states that he defined, especially in the case of 2-qubit systems, they are convex combinations of the singlet and the maximally mixed state. They became some sort of paradigm for us to understand why non-locality and entanglement are not equivalent resources. So the most recent results, we know that these states are separable if this parameter W is smaller than 1/3. And we know that states are local if this parameter value is lower than this value of more or less 0.68. This is a result by Marco and co. Also, we know that these states, they violate a Bell inequality if this parameter is slightly less than √2/2. In this gap here, from 0.68 to 0.7, we don't know. We don't know if these states are local or if these states are non-local, if these states violate some Bell inequality. The Bell inequality that Thomas Vertesi found to get to this value is a very complicated one. So he already managed to study like many Bell inequalities, and this is the best he could get, like to get a little lower than the value that you get for CHSH. So this is, in my opinion, this is a very interesting problem. This is one of the problems that motivates me to keep working on this area, to try to understand why we have these entangled states, entanglement being truly quantum correlations. Why don't they manifest this quantumness in Bell scenarios? So one of the things I like to do in my research is to try to find some new scenarios, some different scenarios than this simple one where these states can manifest some sort of non-classicality. And this talk is more or less about one of these new scenarios that I like to consider. The second ingredient that you need to violate a Bell inequality of quantum systems is measurement incompatibility. If your measurements are projective, then you can associate them with some observables. And it means that the observables associated with two different measurements from Alice, for instance, they cannot commute. And the same for Bob. So this is also a necessary condition. Sorry. But if you have compatibility of measurements, what does this mean? It means that you can define a joint probability distribution of outcomes for these measurements. This is one thing that you gain when you have compatibility. So if your measurements are incompatible, then you cannot define a joint probability distribution. However, if all measurements are compatible, then you can define a joint probability distribution for all the outcomes of all possible measurements, and this leads to locality. This is a known result by Fine. However, this condition, local incompatibility, is also not sufficient. There are recent results by Thomas Vertesi and Marco Tullio and co-authors that shows that you have compatible measurements that do not lead to non-locality. So we have these two ingredients, entanglement and incompatibility. They are necessary, but they are not sufficient. So I'm going to use this property that measurements that are compatible may lead to joint probability distributions to try to expand a little bit the scenario that I'm considering. So now I'm going to work in this scenario. I have Alice performing 2 measurements, and Bob performing 4. And all the measurements are dichotomic. They have only 2 different outcomes. From my previous 2 slides, or 3 slides, I showed that, Stefano Pironio showed that independent of the number of measurements that you have in one of the parties, the only relevant inequality is CHSH, right? So the only relevant inequality in this scenario is CHSH. It's proven. However, I'm going to assume that my measurements in the Bob side are 2 by 2 compatible according to the rules given in this square, meaning that measurement 0 is compatible with measurement 1, measurement 1 is compatible with measurement 2 is compatible with measurement 3, and measurement 3 is compatible with measurement 0. So I can jointly perform these measurements. I'm assuming they are compatible. I can jointly perform these measurements, and I can define a joint probability distribution of the outcomes of these sets of compatible measurements. So I'm going to define these sets. These are the contexts that we saw in Barbara's talk yesterday. So these are the contexts I can define in my problem. So I can press like 2 buttons at the same time because I'm assuming these things are compatible. Okay, so I'm gonna change notation. I'm gonna use these Y with a bar and a B with a bar, saying that I'm pressing actually 2 buttons now, and I'm getting 2 bits as answer. So I'm getting an answer, an outcome for one measurement and an outcome for the other. I can distinguish them. Okay, so I know which outcomes from each measurement. Then I have a new object. Before I assumed the compatibility structure, I could only talk about the probability of having outcome A and one outcome B in Bob's side for X and Y. Now I have a new object. I can work with this object. I have the probability of obtaining outcomes A, B, and B prime, given that now I make measurements X, Y, and Y prime. Given that Y and Y prime are in this, well, I'm pressing according to these compatibility rules. Okay? So this is how I've already imposed a strong constraint, but this is how I have a gain. So now I have a new object, I can study this object. Now I want to look at non-locality in this scenario. Actually, this scenario I can realize in a tripartite way. This is completely equivalent, not completely, but almost equivalent to a party Bob performing two dichotomic measurements, and he performs 0 and 2, measurements 0 and 2, and then a third party performs measurements 1 and 3. This is the same. This scenario realizes this compatibility structure. But I want to be more general than this. I want these 2 parties to be the same. So I'm going to keep using this notation, okay? I want to see these two boxes as only one, because I want to define non-locality here. So for me to define non-locality, I have to first define what is locality. I want to define local correlations between parties A and B as a whole. So I'm going to use a definition very close to the one Bell used. So I'm going to say this object represents local correlations if it can be written as convex combination of a probability of outcome A given X and lambda, and a probability of these outcomes B and B prime, given that I measure Y, Y prime, and I have lambda. Okay, so now I have these probabilities, but even these marginal probabilities, they are probabilities of B, B prime, given Y, Y prime, and lambda. I can have correlations at this side. Is it clear? I can have correlations only in Bob's side, but I don't want my criterion to be sensible to these correlations of Bob. So I want to include these correlations of Bob only in my definition of locality. Okay, so I want even these points that have correlation in Bob's part to be local. So how do I do this? Well, we see that these are convex combinations of points, so I just have to look at the extremal points of my set. The marginal probabilities of Alice can be deterministic. There's no problem. But here, I'm going to include points that are non-disturbing or non-signaling, in some sense, between these measurements of Bob. In this sense, I'm including all correlations that Bob can have in my definition of locality. To be more precise, we know that the set of local correlations is a polytope, and we can define these polytopes into equivalent ways. First, we know that it's a convex hull of a finite set of extremal points. We also know that we can define this set by means of the facets of the set. They are the Bell inequalities. And we can change these representations. So to get Bell inequalities, we start with the extremal points that we can compute, and then we perform some operations and obtain the inequalities, obtain the facets. We change the representation of the set. I have my extremal points. I know what they are. I know that this set is composed of points that are convex combinations of the extremal ones. And the extremal ones are these. These are the probabilities that are equal to 1 if A is equal to some function of x and lambda, and 0 otherwise. So these are deterministic points. These probabilities are 1 or 0. But on Bob's side, I can have either deterministic points, but B depends only on y, and B prime depends only on y prime. Okay, so I don't have signaling between these measurements. So the result of B doesn't depend on y prime. Okay, so these are deterministic points, but that satisfies this condition. But also, I'm going to include non-deterministic points that have strong correlations. These are like PR boxes of B and B prime. So I'm going to include these points in my definition of locality as well. When I do this, they are part of my local set. So correlations in Bob's side only will not violate any of my inequalities. This is good. This is what I want. I want to witness correlations between, non-local correlations between Alice and Bob. So I don't want the correlations of Bob to interfere in this. Okay. If I took, for instance, only these points here, not these ones, then I could have correlations in Bob's side that would violate my inequalities. I don't want this. Okay. When I include these points, then I'm good. Then I'm safe. So that's what I'm going to do. I start with all these extremal points, and change the representation and get the inequalities. So we found 26 inequalities, in contrast to 1 if I didn't assume the compatibility relations. I had only CHSH. Now I have CHSH plus 25 new inequalities. Okay. So we've studied these inequalities. I'm not going to show them here, but they're in the paper if you're interested. As I said, this scenario is very similar to a tripartite scenario where each of the parties perform 2 possible measurements and they have 2 possible outcomes. So not surprisingly, we found that 15 of our 26 inequalities are equivalent to the inequalities of Silva, who studied this 3-2-2 scenario. So this is quite interesting because it shows that some of Silva's inequalities are satisfied this condition of mine. They are insensitive to correlations among 2 parties only. Among our 26 inequalities, we found one very interesting, this one. And we looked at it with a little more care. So you see, we have a CHSH inequality here, but it's CHSH term, but it's multiplying a term that is 1 minus B0. Remember that B0 is compatible with B1 and B3, so it's okay that it appears together. If B0 is equal to minus the identity, then I have a usual CHSH inequality. You see, because I'll have a 2 here, so I have 2 times CHSH, but then I'll have minus 2 here that goes to the other side. I have 2 times CHSH is less than or equal to 4. Then I divide everything by 2. I have CHSH less than or equal to 2. So I get CHSH back in one particular case when B0 is equal to minus the identity. So at least I have CHSH. But can this inequality be better than CHSH? Are there values of B0 such that I can violate this inequality with states that do not violate CHSH? So this is the question that we made an effort to answer. And to realize these compatibility relations, we went to a scenario where, to essentially a tripartite scenario, but still a bipartite one. I have a Hilbert space of dimension 2 in Alice's side, of dimension 4 in Bob's side, but measurements 0 and 2 I'm going to perform in in a subspace of dimension 2 that is tensored with a subspace of dimension 2 where I perform measurements 1 and 3. So I have these compatibility relations given by this tensor structure. This is not as generous as I could get, but this is easier to implement. And now we're going to look at families of 2-qubit states. However, this state is a 1-qubit, 1-q-quart Hilbert space. But I'm going to embed my 2-qubit states there. So I'm going to just take these 2-qubit states and embed them trivially in this space. And now I'm going to optimize over measurements to see how these states behave in terms of this inequality, if they can violate them. I'm looking at regions of parameters where states do not violate CHSH inequality, but do violate this inequality, and we find it. So our first example is this family of states. These are states that are the states that are most entangled, but do not violate CHSH inequality for some parameters. Okay, so here it's a 2-parameter family of states. I can change this alpha and I can change this W, and we found that CHSH, they do violate. Well, for each value of alpha, I can look for the minimum W such that these states still violate some inequality. So we first tried CHSH. For CHSH, we have a criterion, the Hordecki criterion, that is necessary sufficient for violation of the CHSH inequality, and these are the black dots. The black dots do not appear here because they are covered by the blue ones, but the black dots are the critical parameters, the critical H's in terms of alpha, such that these states violate the CHSH inequality. Then we tested the I3322 inequality. I3322, we know that it's better than CHSH for some states, and in particular for these ones. So, but not in all region of parameters. So we optimized over the I3322 inequality as well, and we found this blue curve. So it's better than CHSH in this region. And now we've done this for our inequality, the one that I showed in the previous slide, and these are the red dots. So our inequality is better than CHSH for the whole region of parameters, but not better than I3322 in some region. And of course, these are upper bounds on the real critical values, because I made some assumptions on the measurements that I'm making, in particular that they obey this tensor structure. So they do not need to do this. But anyway, our inequality is truly better than the CHSH, in particular for this point here, when I have a maximally entangled state mixed with this orthogonal state. So we see that there's a huge gap between our inequality and CHSH. Yes? No, I have 1 qubit in Alice, 1 qubit in Bob, but I'm embedding this qubit of Bob in a 4-dimensional space. Okay. It's always in a 1 qubit subspace. I said, great. Now let's try Werner state. Maybe we can lower the parameter. So let's change this this noise here, this pure noise here, to a white noise and see what happens. Well, Werner state is when the alpha is equal to 1/2, but then I can change this parameter. I have this family of state as well. It's good, but not so good. Unfortunately, I could not make to lower the of the Werner state, but still, our inequality is at least as good as CHSH. Is better for some region of parameters. And I3322 for these states behave exactly like CHSH. So the CHSH points here are the same as they would be for I3322. So also for states of this family, our inequality is slightly better. So to conclude, in summary, what I've shown you is that measurement compatibility is not necessarily a drawback. It imposes strong constraints on the measurements that we're performing, but these constraints, they're not all. Like you have more possibilities, and these possibilities can lead you to new and better Bell inequalities. In particular, in this scenario that I presented you, of course, this is a particular one. We could apply this framework to any compatibility relation that we wanted. We can just construct a graph of compatibilities and then do everything again and obtain new inequalities, you know. But in this particular scenario that I showed, we already got 25 inequalities. That's, well, 26 in total, but as compared to one, that's one you obtain when you don't assume that you have these compatibility relations. Depending on the assumptions, the inequalities can be tested in a device-independent manner. I say this because in this particular scenario, you can implement it in a tripartite Bell test, and this is device-independent. Okay, as long as you well, it has to do with this next point as well. Since in this scenario, it can be implemented in a tripartite way, and we saw that, in particular, the inequality that I showed is one of Silva's original inequalities, that you can use, actually, multipartite Bell inequalities even to test the non-locality of bipartite states, as long as you're okay with saying that a state of a tripartite system is actually bipartite. I mean, as long as you're okay with combining particles of and saying that the state is bipartite. That's why I put the asterisk. And this framework is also suitable for the investigation of Bell non-locality together with local contextuality. Because now I have this object that I can treat in an equal footing the contextuality in Bob's side, for instance, and in Alice's side. But this is the first step towards something much bigger that I believe, that we can explore these scenarios and see what kind of inequalities arise and obtain better Bell inequality tests. These compatibility assumptions, they're not in general device dependent, of course. It's very hard to implement like general compatibility structures like this. But anyway, you can get some cool new stuff if you make these assumptions. And with this, I would like to thank you for your attention. Questions? Marcel?